one Wi-Fi radio, many roles. We know there are lots of configuration planes are there, different types of MAC architectures are there, and now how Wi-Fi 7 evolution is happening in the Linux space. I would like to invite Shivam Thakur for presenting nuts and bolts of Wi-Fi and OpenWrt. Shivam.
All right, so it was a nice presentation by Susinder, but of course the devil is in the details and how we implement it. And from the implementation point of view, I have a brief content today to explain how the Wi-Fi and OpenWrt and in general Linux space works. So today I'm going to present on the topic called nuts and bolts of Wi-Fi and OpenWrt. My name is Shivam Thakur and I work as a senior software engineer at Plume Design, focusing on OpenSync Wi-Fi. Let me first walk you through the brief content of the presentation that I have today. We will begin with the overview of Linux Wi-Fi and networking subsystem. We will then explore how Wi-Fi 7 has evolved in the Linux subsystem. Next, I will highlight the structure of embedded Linux and show how OpenWrt is designed around it. Focusing that, the fun part, a simple demo of OpenWrt running on Banana Pi R4. And finally, we'll wrap up with some interactive Q&A session. One Wi-Fi, many radios. Most of us know that Wi-Fi communication is half duplex. It means it can either transmit or receive at a given time, quite similar to how we humans interact. But Wi-Fi radio, it switches its role very fast, that we hardly observe. All these roles of Wi-Fi is operated through network device called net device in Linux. We have access point interface, we have station interface, we have monitor interface, we have mesh point interface, and we also have WDS interface. We can also have many more interfaces, which is basically defined in this structure NL80211_IF type. This is basically an enum defined for a user space application to use that what kind of interfaces you want to create on your system. And of course, the availability of these interfaces also depends on how your Wi-Fi hardware is capable. Let's go a little bit on TCP IP and OSI model, because we all have studied this pretty much many times. And we all know that how TCP IP and OSI model defines the flow of the packet coming from the user space, all the way starting from the, let's say, an HTTP packet, going to the transport layer, like a TCP fragment, it's TCP segment, we have IP packet, and then all the way to the .11 frame. But to manage, but this is basically about data plane. You know, the TCP IP and OSI model pretty much defines how the data plane works. But what is data plane actually? So let me give you an example. Imagine data plane is like a car driving on the roads. It's concerned with how vehicles move from point A to point B, the actual traffic flow, lanes, stop signs, and traffic lights. This is what the OSI and TCP IP model describes, the movement of data packets. But to manage this traffic on roads, we need a traffic management team. They decide which roads are open, where to build the new lanes, when to change the traffic signals, and which routes cars should take. This is called configuration plane or control plane. The control plane sets up the rules and policies, but it's not moving the cars itself. So while the OSI and TCP model explains the journey of cars, which means in Wi-Fi it's data, it does not explain how the traffic rules are configured or who decides the route. That's called the configuration plane. So let's understand what is the configuration plane. Any user space application basically interacts with the kernel space broadly using these three mechanisms. One of the mechanism is system call, then we have netlink sockets, and we have virtual file system interfaces. These are just the broad communication methods that any user space application use. So let's boot up. Any Wi-Fi radio connects to the system via PCIe or USB, or maybe it is part of a SOC already. When system boots up, the Wi-Fi driver actually registers this Wi-Fi radio, and then how it registers this PHY device and creates the instance of a struct called struct Wi-Fi and populates all the necessary fields into it. Until now, we don't have any interfaces created on the radio. So let's create an interface on the radio. You can create an interface on the radio basically by using this command called from the IW, and you can also specify the type of the interfaces that you want to create, like as I mentioned in the earlier that there is an NL80211 IF type. It sends the command NL80211 new interface, then Netlink runs this add interface command and passes it to the CFG80211. This is a very interesting thing, CFG80211, to register a virtual interface. This is finally heard by the MAC layer or the driver itself, and they finally allocates the wireless dev structure. Now, what is CFG80211, right? Let's go a little bit more further on that. So IEEE defined two key management entities, which is called as MLME and SME, which is like MAC layer management entity and station management entity. MLME provides essential services to control and manage the PHY, while SME coordinates operation across MLME and PLME. PLME is PHY layer management entity. But from the user space point of view, host APT and WPS supplicant are primarily responsible for doing SME and parts of MLME. They talk primarily to the CFG80211 via NL80211. NL80211, as I said, was a communication method to talk to kernel space. And CFG80211 stays in the kernel space, listens to all user space applications. Now, this is a configuration interface between user space and Wi-Fi driver. What? The CFG80211. Netlink provides notification to the user space about various events. But what happens after CFG80211? There is a MAC layer management entity and there is a MAC 80211 defined in the Linux kernel space. And it also listens from the CFG80211 interface. By the way, any Wi-Fi driver can directly talk to CFG80211. But a Wi-Fi driver can also talk to MAC 80211. Then finally, as I said, driver will come into the picture and driver operations, and all the implementation of driver is done in the driver layer. Now, this is a typically kernel space to user space path, like how the kernel space is sending the commands. So for example, channel switch announcements, how you basically trigger a scan, how you get the scan results. Those are basically a notification that is coming from kernel space to user space, and any application who is listening to those events can see those events and do all the operations that they want to do based on that. Next, we have user space. So user space to kernel space path. So in this, we have a structure defined, WPA driver underscore NL80211 ops, which is nothing but the set of operations that a user space can do, and they can speak with the CFG80211. So this, in this case, I'm just explaining how you host APT sets an AP. So there is a set AP function that is running by the Netlink, and it eventually comes to the CFG80211. And what CFG80211 does, it simplifies all the configuration and coming from the user space, and it has another set of callbacks defined further for the driver or the MAC layer. So let's see some examples. CFG80211, let's say, exposes a start AP function. It has change beacon, stop AP, add station, delete station, change station, and many more standard functions defined as a callback, which a driver can register itself. Now, until now, we have seen that CFG80211 is here. And I also mentioned that there is a driver which can listen directly to the CFG80211, but some drivers are implemented in such a way that they speak with MAC 80211. Why is that? So there are two types of drivers. One is soft MAC drivers, one is full MAC drivers. So on the left, you can see full MAC drivers, which directly speaks to CFG80211 callbacks that I showed in the previous slide. But there is a MAC layer implementation done in the MAC 80211. And why is that? Why do we need to have a MAC 80211? So let's come and understand why we need MAC MAC 80211 when drivers can directly speak to CFG 80211? Well, again, the devil is in the details. For full MAC drivers, it is essential to implement 80211 MAC logic, association, roaming, aggregation, rate control, block ACK, etc. within the driver itself, which is large, hard, and vendor-specific logic can vary from system to system, essentially maybe causing some interoperability issues due to some difference in implementation across the vendors. Now, MAC 80211 saves an effort for drivers to implement common MAC layer architecture, and it is responsible for authentication, flows, and some frame building, parsing, scanning, and beacon handling, power save, aggregation, rate controls. All those things is done by the MAC 80211. Now, which is why we have a MAC 80211, which exposes essential 80211 operations again back for the driver after processing the common logic for the MAC layer. And drivers such as, in this case, I am just showing an ATH11K driver, which is from Qualcomm, open source driver. And then it has its own callbacks implemented in their type. For example, one of that you see is like a HE scan, hardware scan, cancel scan, set key. And there are many other callbacks that driver needs to implement on its own. Now, let's understand. What you see here is the full picture. Host APD and WPS supplicant are not the only user space application that talk to the kernel space. We have also net IFD, IP, TCP dump, IW, BRCTL, ifconfig, and essentially OpenSync. Let's go little bit more detail in the MLO layer side. How Wi-Fi 7 MLO evolution is done. As of now, today, most of us think that Wi-Fi radio is a physical layer and interfaces are the roles that they operate on. So interfaces sits on the top of the radio. But this interpretation is not valid because the correct interpretation is that a network device in Linux uses the single radio as a PHY medium. But in case of MLO, a network device is registered in such a way that it can use more than one radios as a PHY medium, which confuses the way we were hallucinating about the idea of logical interfaces in Linux. So here, as you can see, this is a new implementation done in Linux 6.6, where you will be only having one single logical PHY, and it has the one interface which can use multiple links, radio 0, radio 1, radio 2. Okay, so let's go to understand how OpenWrt architecture is implemented. Typically, an embedded Linux, or let's say is an operating system which is customized to run an embedded systems, very much tailored for specific hardware. On the OpenWrt is one of the embedded Linux implementation. So any embedded Linux, what you need? We need some key components. We need a bootloader which boots the system. We need a Linux kernel. We also need a root file system. We need a C library. We need init system. We also need user application. So Linux kernel, you know, bootloader, I think most of us know. Root file system is basically how you arrange your directory structure and do things inside that. C library is used for compilation and toolchain. Init system is how you want to align the process and how you want to sequence this processes around it. And of course, the user space applications, which is like nothing but applications that you see in the App Store. It's kind of an App Store for OpenWrt. Now, how you create a custom user space application or a package in OpenWrt. So we have user space OpenWrt/package, where you have different categories where you can put your user space app. You have the network category, firmware category, you have the kernel category, libs category. In each category, whatever category package you are creating, you can put inside it, and then you can, all you need to know is to know how to write a make file which can compile or cross-compile across all the platforms. And then here you go. Now, here's the fun part. So I was just little bit playing with Copilot, and I was just trying to see how we can create some fun application out of the Rust implementation that I did. I created a Rust package, and then I also created a thing in the AWS IoT Core. It's a cloud solution for that manages the MQTT side. So I'm just using the MQTT part of it. So I created this thing in AWS IoT Core. I also had a banana pie, and Rustify is the name of my package that I have created. What it does is it collects the connected station matrix or statistics from the kernel space of all the stations, and it passes that to the AWS IoT Core. And then I have created this kind of a dashboard. This is like something that Copilot has created, and I have just customized based on the things that I have given to him. So it collects all those statistics and plot the things accordingly. So let's see. So if you see, I am running the Rustify on the terminal, and as soon as I run, 3 clients are already connected, and you can see they will be showing up here in the user. And all these lines you see are the RSSI for the per antenna. 3 red antennas, 3 blue antennas for 2.4G and 5G. And you see the red color because the RSSI on that antenna is not good, and yellow color because it's little bit okay. And now I am just changing the attenuation to increase the distance. And what I'm getting here in this demo is that when I increase the distance, you can see in the application, pretty much immediately you should see, yeah. The distance is increasing, the lines are going red because the RSSI is poor. And this is just a fun application that I just played around. So the implementation is like a Rust application that is running on the user spaces using Netlink to collect the statistics. It is then sending again back to the cloud. From the cloud, you have a nice visualization tool that you can do, and you can do some research using this. You have all the full stack available: OpenWrt, user space, kernel space, cloud. You have the lot of AI tools to implement things on top of it. So this is one of the example that I did. You guys can try your own example because you have all the tools that you need to do. Okay, all right. So I think we are now ready with the Q&A.
Questions?
Shivam, thank you for an excellent presentation. I think the information that you shared, it's very difficult to gather it just by scraping the web. Thank you very much for that. I just wanted to check, is Banana Pie available in India for us to procure locally, or any alternatives to?
So basically, I purchased it from one of the application. I think I have that app in my phone. It's basically a way. This is a new app like an Amazon. You can purchase this banana pie. I just bought it from 32,000 rupees, and it came all the way from US to India. And I think I will tell you the name later. You can just reach out to me. I'll show you.
Okay, thank you.
Okay, next question. With the interest of time, Shivam, I have a question for you. So, shall we integrate AI ML based optimization like dynamic channel or TX power tuning directly into OpenWrt packages, or that should just stay outside the kernel or user space?
I think kernel's main role is to manage the hardware, and I don't know where the community in kernel space is going towards the AI and stuff, but most of this logic should stay in user space. Of course, there are some mathematical computation algorithms that are currently being performed in the kernel space, such as aggregation and stuff like that. Maybe we can use, let's say, a simple example like maybe the moving average algorithm you have in mathematics computation. Try implementing in user space and see if some of these algorithms, let's say RSSI average, average RSSI you are getting from collecting the last RSSIs and you're averaging it out. So maybe you can implement some mathematical algorithms and then merge them to create some sort of computational, because it's all about computation. That's it. And I think another great thing we can do, which I was like discussing with some of the folks, how we can have an inter-device communication from kernel space of one system to another system for the user space applications. So that is one of the key area that we can target for the distributed computing.
Okay, any last minute question? If not, please give a round of applause for Shivam. Thank you, Shivam, for your excellent